The problem with OFDM is that every carrier has a different modulation, and therefore the peak could be very high, the average could be very low, and the ratio could be anywhere. Peak to average ratio, pepper. Peak to average power ratio. And if your peak is, you have to design your amplifiers for the peak, because after that they are non-linear, so you have to make sure that you get an amplifier whose linear region covers the peak. And if your average is very low, your quality of the signal is going to be very low. I mean, basically you're going to have low signal to noise ratio. So you really want to keep the average high. And so they said SC-FDMA will do that, single carrier FDMA. And single carrier means that you don't have 200 carriers to worry about. You just modulate it with whatever symbol you have, and you have the peak and you have the average. So basically we take user 1, give them some wide carrier, and then user 2 another wide carrier, user 3 another wide carriers. Now normally in OFDM each subcarrier might be 15 kilohertz apart, and this might be maybe 10 times that. Okay. So, and then they add a cyclic prefix, etc., and that is supposed to give you better pepper. It turns out it's not that different in practice, because it is also implemented with FFT. What they implement is, so if this was suppose equal to 10 subcarriers, they would do exactly that. They would start with symbols and then serial to parallel. Now this is all, remember, this is all in the memory, so there is no real analog or radio signal here, but it's just memory locations. So you have a QAM symbol, you make serial to parallel, you take M of them, where M is the number of subcarriers or width of the band that is allocated to this user. Do the FFT. Now what FFT does is changes Fourier transform. What it does is it changes from time to frequency. Okay? When you take a Fourier transform of a signal, it changes from time to frequency domain. So now you have frequency domain. So here they are basically different carriers. But again, these are not real carriers, these are some memory locations. And then you put the rest of the carriers at 0, and you do IFFT, that becomes time domain again. When you take a signal and you do inverse fast Fourier transform, you go from frequency to time. So you are in time domain again, and then you just do parallel to serial. So these are coming in parallel, you put them on the serial, so now you get one sequence of symbols. You add the cyclic prefix to those symbols and you put them on the antenna. All right. At the receiving side, which is actually in this case is the base station, we are talking about the uplink. At the base station, you remove that CP, do that serial to parallel, do that FFT. Now this was IFFT last time, so it was time domain. Now we do FFT, so the time becomes frequency domain again. Now these are all numbers, by the way. This whole thing is number. The analog part I have not shown, but basically there's an antenna, from there there's an amplifier, and there is a D to A converter, A to D converter. And then once it becomes D, which is digital, then we just use this memory thing, right? So then you convert back into time domain, FFT, time to frequency domain. Now these are all carriers, or carrier memory locations. Then you demap them, because there was a mapping here. Mapping, what it does is it randomizes, put the symbols at different places. So this is a demapping. And then you take the carriers belonging to the user number 1, user number 2 separately. And then you do IFFT. So that becomes, okay, so this is time, frequency, time again. All right. And then you do the demodulation or whatever you need to do. You get the bits, user bits. So notice these two things I have circled. That you have an FFT here and you have an IFFT corresponding to that here. If it was not SC-FDMA, if it was OFDMA, and we have shown you FDMA again, but I will show you one more time. If this was OFDMA uplink, then what will happen is the user 1 will, when it gets the signal, it will have these time domain things. It will put them in parallel, and then mapper, and then IFFT. So these are carriers, okay? So IFFT will make a time domain and it will be sent. And then when it is received, time domain, FFT will make frequency domain, and then you do the equalizer and whatnot, and then you do demodulate them and you get the symbols. So if you compare between the two pictures, I'm going to come back and forth. This picture and this picture, what you see is that those red boxes are missing. Everything else is similar. This, there is no FFT, there is just simply IFFT at the end. And there is no IFFT, it's straight away connector after equalizer to PS. You see equalizer to PS, and then there is no FFT here. So what does that mean? Why? Actually, so I remember back in 2010, this was the topic of debate because LTE said we are different from WiMAX, and we are different from WiMAX because we do this single FDMA, single carrier FDMA, which is much better than OFDMA. It is much better than OFDMA because we are have low pepper and all that. But actually, this is OFDMA very similar, except that what we have done is before we give the carrier to the mapper, we do DFT, discrete Fourier transform, which is another name for FFT. So discrete Fourier transform, DFT pre-coded OFDMA. So basically, instead of giving plain carriers like here, we pass them through a DFT. That's the only difference. Okay? So this is DFT pre-coded OFDMA. SC-FDMA is same as DFT pre-coded FDMA. Now, is this clear? The last sentence. And that's why I put these two slides next to each other so you can see. This picture and the previous picture are identical, 15 and 16, slide 15 and slide 16.
Sorry, we don't have the 15 and 16, the older version.
Just take the whole hand out. We have 3 copies if you need one more. All right? Okay. So, channel dependent scheduling. So we are done with the modulation part. Now we are going to go through. Other features of LTE. And the reason I want to go through these features of LTE is so that you know what is the latest in wireless networking. Okay? And these features are not just in LTE, but anything that is developed today will have these features. Okay? In particular, WiMAX has this feature too. I mean, so the idea is that, so one thing that they do is channel dependent scheduling. What that means is schedule users at their best frequencies and times and optimize overall throughput. So I think I explained this before last time. Is that you ask each user, what is the best signal you're getting? And he says, I'm getting best signal at the top, these subcarriers. So we say, okay, you get those subcarriers. Ask the other user, what you are getting best at? And so everybody reports their, what we call signal to noise ratio, and we give them their best. So that way the overall throughput is maximized. Everybody can use, high modulation rate then, and they can, okay. Focus transmission power in user's best channel portion. Okay, so I mean the channel is so wide, but we cannot give the whole thing to one user, so we give each user a piece, but give them the piece which is best for them. Adaptive modulation and coding of each individual subcarrier. So we basically give them the highest modulation that they can support for that signal to noise ratio. And by randomly distributing subcarriers over the entire band, and that's another thing we do, 4 things. So now these are very common, but basically, so suppose we give you 5 subcarriers, then we might just distribute them all over, unless there is a reason for you to just give you those particular ones. If there is no reason, then we just distribute all over. So that way, you are not subject to a noise in a particular area. You will get some good, some bad. So here is an example of giving the best. So user 1 says that this is my SINR. I have the highest signal to noise interference and noise ratio at these values. So they get the red carriers. This user says I have this form, and so they get the blue carriers. And this one says this, so they get the green carriers. Okay, everybody gets the best that they can get. Also, we have to weigh against this how much data they have to send. If somebody has more data to send, we can give them more carriers. If somebody has less data to send, we send them less carriers. So there are lots of complication in doing this. And so there are interesting scheduling and fairness issues. I mean, if you give somebody the whole band, they say, oh, I'm very close to you. I'm just sitting next to the base station and I have everything good. You cannot just give them the whole thing. Right? So that will be a fairness issue. So then there are lots of papers on scheduling. By the way, we also did a paper on scheduling. So that's a good top PhD thesis topic. And so basically there are lots of papers on that issue. Scheduling, fairness, efficiency, trade-off, and all that. But basically the idea is that we give each user the best part of the spectrum that for them is best. Clear? Now, when you give them some carriers, we already talked about that we give them the best part. In that case, you don't have a choice. You just give them contiguous. But if you have a choice, then you distribute them. So for example, the blue user gets, let's say 10 subcarriers. Actually 12 to be exact. Let's say they get 12 subcarriers, we give them this distributed all over. The red one gets this, and so on and so forth. The black one gets the other one. And so everybody has, almost different places. So if there is an error or noise or something at this place, one person is not wiped out. Right? So that is called distributed subcarrier allocation. The other option is to have contiguous subcarrier allocation. In the contiguous case, all the reds are given to red, this is all given to blue, this is all given to black. And then we hop, in the sense that in the next slot, we might move the reds to here, the blacks to here, and the blue to here. Now, for hopping, again, there are two considerations. One is that we have information, and in that case, we just use that information to where this would go. Or if you have no information, we just randomly hop. So nobody is left at one place, at the wrong place permanently. Now, none of these actually I know are there in 11, 822.11 right now. But you see, this is the latest technique. And if the next version of 11 was to come where they are using OFDM, they will do this. So everybody understand these two methods of distributing the noise everywhere. Basically, the idea is that you don't want to fix somebody at one place and then they be victim of noise in that frequency domain. Puncturing. The puncturing idea is that you could use a very good ECC. Very good ECC means lots of ECC bits. We saw code rate 1/3. What code rate 1/3 means? That for every one bit, there are two ECC bits. So instead of one bit, we send 3 bits. Right? We saw 1/4, 1/8, and so on. So you send lots of ECC bits. But somebody realized that you really don't have to send them. You can compute them and just send some of them, not all of them. And since these are error correcting code, they should be able to correct. Right? So what you do is, let's say these are the two data bits, D1 and D2. You use a half code, which means that you put 2 more bits, E1 and E2, so 4 bits. But you're not going to send all 4, you're going to send 3 of them. So you just selected that I'm not going to send E1, I'm going to send 1/4 puncturing, means I'm going to send 1/4 of the bits. So out of 4, we are going to send 3. D1, D2, and E2 we decided, right? Of course, the other guy knows that you are sending D1, D2, and E2, by the way. So they know what is missing. Now, the other guy generates a random number and puts right there, random bit. So it gets the 4 bits. Now it tries to do the error correction and finds D1, D2. right? Some possibility of getting it R1 wrong. But the CRC will not match, and then they will know that this is wrong, right? So the idea is you don't have to send all the ECC bits, and that this is called puncturing. All right. Any question about puncturing?
Why not just use one and collect the quota?
Okay, that's a good question. Why just not use it? If you're going to send one bit, just put one bit error correction, one bit ECC, and one bit ECC in general will do better than using 2 bits and puncturing out 1 bit. Okay, but there is something which is coming up. So the idea here is, which is coming up, and I'm going to tell you again one more time, is that the idea is that, okay, we won't send you 1 bit, but if you get into trouble, then let me know and I will send you that 2nd bit. So the 2nd bit is sent, the missing bit is sent if necessary, which is 1%. Right? 99% of the time you are okay, but sometime you might need that bit, and I will send you that bit. All right? Which you cannot do if you were going to just have 1 bit, then what do you do? Right? So you compute it, but you don't send it, and if they ask, then you say, well, all right, here is the bit. Okay? So to explain that concept, I have to explain you the concept of ARQ. How many people know what is ARQ? Just 1 person? 2 persons? Harith, did you take the 473 here? No? You? Here, was you? And they didn't teach you ARQ? Okay, anyway, this is a kind of sometimes unbearable that, such as key concepts are missing, and we spend all the time on CSMSCD. But the idea is ARQ is simply automatic repeat request, is that, if you get an ACK, you send the data, or if you don't get an ACK, you send the data. So that is retransmission. Another name for retransmission is ARQ. You send the data, and if the receiver finds an error, it says, sorry, I didn't get that bit, and then that packet, and then you send the whole data all over again. Right? Until you get the acknowledgement. That is ARQ. Normal ARQ, which is done on the wired networks, done on the wireless network, does in TCP and everywhere. Right? What is wrong with that? The thing that is wrong with it is that I might have gotten 90% good bits first time, but I'd make no use of it. 90% is no good. We just throw away all those bits. Somebody came up with the idea, look, on the wireless, we have to be very careful. We can't just throw away 99% good bits or 90% good bits. Let's keep them and then get some more good bits to make up 100%. That is called hybrid ARQ. In hybrid ARQ, suppose I send you data with half puncture, means whatever, I just gave this is an example, is that I send you only half of the bits. Right? Other halves are missing. And you say, sorry, I didn't make it. Then I send you another quarter puncture. Right? Maybe you will make it. Because now you combine these bad bits from before. You have some missing, you are putting some random numbers there. You put the actual numbers there. Now you might be able to do it okay. So you combine the old information and the new information and then decode. If it's good, you say, okay, I got it. Right? So basically you don't throw away the bad information. You keep actually it's not really bad, it's just that you don't have enough information. So you take the old information and then you transmit some more, and you are able to decode it, then you are all set, and then you save some. So here we saved 1/4 at least, even though it took a little bit time. But most of the time you will be happy with just first one. Half will do okay. So this is called HARQY because both phi and MAC are involved. The phi knows which bits are missing and how to combine the bits, because all this coding, decoding is not MAC's business, it's all the phi's business. So the phi does that part, and the MAC simply does the CRC and says, oh, this is not good. All right. So this is called hybrid. This is why it is called hybrid ARQ. What that means is that the MAC tells you that it is no good. Phi says, okay, here is more information. Is it any good? And if it is good, it's fine. If it's not, then phi gives you even more information. Even more information. Okay. Any question about HARQ? All right, there are two types of HARQ. One is that you do, like I said, you give partial information and then you keep adding. This is called incremental redundancy or type 2. This is incremental redundancy. But it turns out you don't have to even do that. You could just send the same data again. Now, first time, some bits got hit and they were just on the boundary line between 0 and 1, and you couldn't figure out whether to put a 0 or a 1 there. Second time you send the same bit again, hopefully some other bit will get hit, and this bit will be very close to 1 or 0 where it is supposed to be. So you take those two phi signals and figure out which is really, good value for this particular bit and combine them. Even that helps. So that is called chase combining or type 1 HARQ. Here, you just send the same data again. So, what did you save over ARQ? Well, you saved a lot because even though both packets are in error, you have a good packet. If it was ARQ, you would have required a third transmission. Okay. Now again, HARQ is in BiMAX, is in LTE. I don't think it is there in 11s. So, this is all latest thing which are happening, and it will be there in all the latest version of all the protocols. Okay, clear HARQ? All right, coding. I had talked about a space-time block code before, but since it was so long ago, I just thought so long ago in this semester that I thought I will just flash this slide all over again. Is that if you want to send two symbols, let's say one symbol is S, X plus IY, and so in this case S1, which is X1 plus IY, complex symbol, right? Because you have amplitude and phase. So you have the real part and the imaginary part. So you have two symbols. So Alamuti, Wahid Tarok actually. Wahid Tarok found out that in 1998 that if you have two antennas, what you should do is on the antenna first, you should send, on the antenna number 1, you should send S1, and on the second antenna, you should send minus S2 star, where star is the conjugate. Conjugate means if you have X plus IY, the conjugate is X minus IY. Reflection of this, if you take this point, reflection is right here. So that is conjugate of S. So you send the S2 conjugate here, minus S2 conjugate, and the second slot time, you send, slot time is here. So let me say, on the second antenna, you send S2 and S1 star. So this is antenna 1, this is antenna 2, this is time 1, this is time 2. All right. You see, these are 4 values. Now these are almost the same thing. If you made S1, if you got S1 wrong, this S1 star will not come out, okay, because then you will say, no, this is not conjugate of that. If you got S2 or any of these symbols wrong, then this will not come out, okay. So you have this built-in error redundancy. So with this, you have very high chance of making the symbol, although your rate will not go up because you just send 2 symbols in 2 time slots. So your rate is just 1 slot per symbol or 1 symbol per slot. But your probability of getting it right is much higher now. So your effective throughput goes up. And so this is called space-time coding. Why space-time? Because antennas make up the space. You could have many, many antennas, one here, one here, one here. So that is the space. And the time because you are doing on one slot, and then second slot and third slot, so that is the time. So this is called space-time code. And this is now common stuff. Although invented in 1998, this is the latest thing. Again, both WiMAX and LTE do it. Another way to look at this STBC is in the format that we have been looking at, for OFDM. You have 4 symbols, X1, X2, X3, X4. You first make the conjugates as you need it. So you put X1 here minus X2 star, then X3 here minus X4 star, and then you put X2 here, X1 star, and so on and so forth. So this is what you were seeing in the previous slide, right? X2 star, X1, and so on and so forth. So this is what you would have sent if you in the previous picture here, right? Now what you do is you send this on one antenna, you send this on the second antenna, and you have the same IF, FT, FFT stuff. So basically these two will go on one carrier, the second symbol will go on the other carrier. So this in the multi-carrier case, this is how you do it, okay? The important part is that we are putting both the symbols on the same carrier and both the symbols on the same carrier. So all 4 symbols are on the same carrier. By the way, this carrier is same as this one. So this is the first carrier, this is second carrier. This is the first carrier, this is second carrier. This is the same carrier, just 2 different antennas. Okay. So on the same carriers, we put the 4 symbols, just like here. All these 4 symbols are going on one frequency, but different antennas and different time. So this is how you do it. Basically, is if you want to do STBC in an OFDM symbol, you just put them on the same carrier, different time slots. These are obviously time slots because they're sequential, and then different antennas. But then somebody came up and said, well, what if we did it on the frequency instead of time? So then they came up with another code called Space Frequency Block Code, SFBC. So instead of time, as here, we have carrier and carrier 1, carrier 2. And the exact diagram for this would be that you bring all these 4 as before, but put X1 here, X2 star on the second carrier, X2 here, and X1 star on the second carrier. So basically, now instead of being horizontal on the same one carrier, these are on 2 carriers. Just look at this for a minute and see how this is different from the top, is different from the bottom. In the top, the symbols are separated in time. In the bottom, they are all on the same time, but they are separated in frequency. Can everybody see that? That this is frequency separation of X1 and X2 star. This is the time separation of X1 and X2 star. So this is called Space Frequency Block Code. This is another technique which is used now. And by the way, when I was working on WiMAX, I don't remember seeing a space frequency block code. Maybe it was there, but I didn't see it. But space-time block code was there. Okay, this is very new stuff, and so it is all there in LTE now. Frequency shift transmit diversity. This is another technique to increase the throughput. Is that instead of using too many carriers and putting low power on each of them, because the total power is limited, we have only so much battery or whatever in the mobile. So you don't want to use 4 carriers, you just use 1 carrier and put all the power on that one. In the next slot, you use a different carrier and put all the power on that one. In the next slot, you use a different carrier and put all this power on that one. So this is using the same power as that one. But this has a higher chance of making it. Right? So this is called frequency shift transmit diversity. We shift the frequency every time. And we don't use all the frequencies. So these are sent as zeros. Another technique is, of course, multi-antenna. And when you have multiple antennas, there are many things you can do. First thing you can do is transmit diversity, which is that you put them on different carriers at different time or frequency shifts. So the three things we have seen is before in the previous three slides are here. Space, frequency, block coding, or frequency shift, transmit diversity, or even STBC. So all that is transmit diversity. Then you can do beam farming, which is basically that focus in the direction of the receiver, and the receiver does the same thing. It focuses the ear in the direction of the transmitter. So even the reception is directional. So that is beam farming. Spatial multiplexing is that basically MIMO, where you send multiple antennas input and multiple antennas output, and the signals are somehow separated out. But then there is, so this is actually, we discussed that, but then there is multi-user MIMO, where people don't have multiple antennas, but multiple people can combine together, join together to make multiple antennas. So I'm going to explain these other concepts in the next few slides. But on this slide, you should at least understand the first one, transmit diversity, which I already explained. Those three coding, SFBC, STBC, and FSTD, all those things are transmit diversity. And then beam farming, and okay, so now, and MIMO. If you have a single antenna, and this is called SISO, single input, single output. And in the case of either OFDM or SC-FDMA, whatever, what you do is you put the pilots, let's say at these locations. So X are the pilots. So these are well-known locations. When the signal goes there, by looking at the pilot, we can figure out where it is coming from. Right? When you have single user MIMO, let's say there are two antennas here and two antennas here. Now what will happen is each of this antenna will use a different locations for these pilots. So by looking at these pilots, I can figure out here that this signal is coming from that antenna, or this signal is coming from this antenna. Okay, so pilots are the ones that allow you to really figure out the direction. And then you can separate the symbols basically, so you can get twice as much throughput. Actually, in this case, you have twice as much throughput you will get if you have two antennas. Now, what if you don't have those two antennas, you have only one antenna? Then what you can do is, you can have two users, each with one antenna. But again, the same pilot game is played here, so that one uses X as the pilot and one other uses Y as the pilot. Right? So when the signal from this user goes to these two antennas, it knows that it is coming from Y, and which signal is coming from Y, and this one similarly knows which signal is coming from X, and they can be separated out even though they are on the same frequency at the same time. But once we know the matrix, by matrix multiplication, we can separate out the two signals. So this is called multi-user MIMO. I had shown this picture before to you guys, multi-user MIMO picture, but at that time it was not really clear to you what this diagram looks like and what these are. So now you know that this is frequencies on the vertical side, time on the x-axis, and so these are 1, 2, 3, 4 carriers, 4 symbols. So basically, for each carrier, there is a location where we put these pilots, and the pilots indicate where it is coming from. Cooperative MIMO is another name, but in this case, the cooperation is on this side, on the network side. This is also called network MIMO. In the network MIMO, the same data is sent to two base stations, and now each of them have one antenna. You see, this base station has one antenna, this base station has one antenna, this user has one antenna, this user has one antenna, but they can do 2x2 MIMO. How? Basically, they will put their pilots at the right place, so each of them will know where it is coming from, and then they can decode it. So this is called cooperative MIMO or network MIMO. All right, so much about the PHY layer. Now I'm going to go to the higher layers to show you the latest techniques in wireless. And so first thing latest is IP. This is news for the carriers. Basically, they didn't use IP so far, but now it's about time. So this is 2G, and if you remember 2G, we had plotted it horizontally like this. You had a base transceiver system connected to base station controller, connected to whatever. And then when the GPRS came along, we put the GGSN and SGSN nodes. So this is showing GPRS, and then we put what we call radio network controller RNC. So this is 2G or 2.5G right there. In 3G, these names were changed, and node B became a little bit smarter. This became RNC for sure, SGSN. So there's not much change except for node B. Now in LTE, basically this is called E node B. E is for enhanced, they are not evolved. Enhanced node B. And then instead of all of this, all of these things are gone, and all we have is basically a gateway to the IP network. And then this mobility management entity, and all this does is mobility management is basically make sure that when you're connected to remote locations, when you're moving around, then we know where you should go next, and which tower you should go to next, and so on and so forth. So the mobility management simply is the handover kind of thing, right? Which is not there in IP right now. So basically, those are the only 3 boxes left. That's why it's called flat. Previously, we had lots of boxes, or at least lots of functions for sure, and there were lots of messages being exchanged between those functions modules. But now we have just this left. So that makes the life easier. Everything goes over IP, even the voice goes over IP, the video goes over IP. Now what happens is, while this is nice, but if somebody has a 2G phone, how they connect to LTE network? So basically what happens is the real network looks more like this. Real network is a hodgepodge of the old and the new. Okay? The real network has the GSM, RAN, it has the UMTS, UTRAN, then LTE, node B, CDMA, if somebody had a CDMA, their thing, and if there is something else, they have their thing. So everything is there, basically. So it's not very easy to just, say, okay, it's flat network, but basically they are moving towards the flat network. By the way, this is called the core network, and this is called the radio access network, RAN. So this is the RAN, this is the core, this whole thing is called a system. So now, just to be clear about this, this is the evolved packet core, EPC. EPC is this part, and this is the radio access network. Actually, so basically the radio access, and the whole thing is system, evolved packet system, EPS. This whole picture is the EPS. The core is only up to here. Core is the backhaul, right? All right. So now we understand EPC. Now, basically here we are just explaining some of the boxes which are here, and I'm going to explain them. So the boxes that are here are serving gateway. So this is the destination, the demarcation point between RAN and the core. So let's look at that picture. Serving gateway is here, and this is the RAN, the radio access network, and this is the core. All right, so not this whole thing is not core. Okay, this is the core. So this is the one that connects the random access network to the core. Packet data network gateway, PGW, termination of EPC towards the internet. So this is the PDN gateway. So this part may not understand the IP addresses. This part understands IP addresses. So this gateway basically translates from whatever it comes from here into something that these people can understand, which might have some cell phone number or IMI number or whatever. So this is the gateway, PDN gateway. Mobility management entity, location tracking, paging, roaming, handovers, all control plane functions are in MME. And that was the MME right here, management entity. And the policy and charging function, which is basically making sure that you pay for your bill, is right here. All right. So, now, what happened here now? No response. Okay. Additional information is in request. I don't need that. Anything available? Okay, all right. So page down, page up, space, nothing. All right. I think let me stop right here. Let me see. We finished this one, EPC. All right, EPC is finished, and then we will continue from here onwards, slide 32 onwards next time.